Okay, good morning to everyone. Maybe some of you it's afternoon or night. And welcome to the first 3DOptix live. This is our first live session with optical developers, and we are going to have a lot of those in the future. It came from a demand from our users as a method to see real good designs, how you do optical design, as well as how to use the 3DOptix software. I invited Keith Meyers. He's an experienced optical design. He's working with 3DOptix for this session, and I would let him to introduce himself. So Keith, please, you're welcome to start.
Thanks, Gil. Hello, everyone, and welcome to the 3DOptix live webinar on aberration analysis. My name is Keith Meyers, and I'm an optical designer. I work with 3DOptix as well as ZMAX, creating illumination applications, troubleshooting optical imaging systems, and prototyping various designs using stock and custom optics. I use companies such as Thorlabs, Edmund Optics, and Newport for their readily available optics for my design, as well as custom optics for higher fidelity applications. So in this webinar, I will be presenting a few basic methods for aberration analysis in the 3DOptix web-based platform. One thing I'm very excited about with 3DOptix is the ability to rapidly prototype optical systems using an extensive catalog of stock optics and share my designs with anybody with a computer and an internet connection. These two factors are really important when I'm working with clients so that they have a way to dynamically interact with my designs and have transparent and easy access to the optical files. Okay, with that said, I hope you enjoyed this webinar. Let's go ahead and open up the project design so we can start. All right, hopefully everybody can see my screen. So we'll start with our project file. Okay, so now that we have our project loaded, we can see our optical system here. We'll zoom in so you can get a good look. I've chosen a Cook triplet for this for the design for this webinar, as it is an easily set up optical system with simple variable parameters and output. The Cook triplet consists of two positive lenses and a negative lens sandwiched in between. So we have a positive lens on the outside and the negative lens on the inside. This well-known design gives you 8 degrees of freedom and can correct for all third order or sidal aberrations. For the variables, we assume that the glass substrate is chosen prior for the proper wavelengths of interest. So the glass is not a variable. Also, we assume that the thickness of the lenses is simply a function of the power of the lenses. So we don't consider this as a variable as well. What we do consider variables for this design are the two lens separations. So between lens 1 and 2, and 2 and 3, and the curvature of the 6 surfaces. So 2 of our surfaces here are going to be flat, so plano surfaces. So we actually have four curved surfaces constituting the 4 powers. All right, so this is a good design to analyze because we can easily show aberrations from a nominal component layout, and we can use stock optics to achieve a quick prototype. However, today we will only be analyzing the aberrations in the design and not trying to correct for them. If you're interested in Cook triplet and how to correct for aberrations using its degrees of freedom, there are many resources online, and solutions can be prototyped in 3DOptix. Okay, so here on the left is our outliner bar. This gives a layout of all the optics, all the objects, light sources, and detectors that we have in our 3D layout. So let's look at one of the light sources really quick. We have quite a few light sources here. They're all relatively set up the same. Some are different wavelengths and some are different field angles. So we'll choose the on-axis field. And here at the top right on the ribbon bar, we are presented with some options. So we can rotate the light source, and we can also change its settings. So for our light source, we're using plane wave top hat profiles. The appearance tab, this is purely cosmetic. You can change the ray colors and some of the other options. For the number of 3D layouts, this is a visual layout raise, so we're using 100. And for the actual analysis later on, we're going to be using 1,000,000 rays for this source. Now, for the analysis, you can specify a total amount or per wavelength. So if this was a polychromatic source, we could specify that we want 1 million analysis rays per wavelength. But since we're using monochromatic sources, we'll just do total. This is going to be a circular beam with a circular ray density pattern with 4 millimeters radius. For the angular information, we can angle this ray off the optical axis, but we do want this one pointing straight down the optical axis, so we're going to leave these. And as I said, this is a monochromatic source, so working with a 550 nanometer source, and we're giving each one of our sources 100 milliwatts of power. The other wavelengths that we'll be looking at later on in the design are 800 nanometers and 400 nanometers. Okay, so the field angles for the light source, actually, let's click back on this guy. The field angles for the light source, we have on axis, we have a 10-degree field, we also have a 20-degree field. So I like to just go into the move rotate selection in the ribbon bar and then change my Y angle from there. So as you can see, if we change that, we go from on axis to an off axis position for this field angle. So it's just a good quick way to change our field angles, and we can visually see what's going on. Okay. One quality of life feature that I like to use is in the View tab up in the top left, we can change the ray color palette. Currently, we have it set to spectral ray colors, so all of the field angles on axis, 10 degree and 20 degree would be the same color. If you have a complicated design or you're trying to see where individual light sources are propagating through the system, it can get a little bit confusing. So we can color these in different ways. I'm going to choose user-defined colors, and that's going to color the rays, every propagation source in a different color. And again, just to reiterate, that is seen in the appearance. So for the on-axis field, the ray colors will be green. Okay, moving on to the actual optics. We've chosen stock lenses from the 3DOptix included catalog. These are readily available Thor Labs lenses. So I'm going to show you really quick how we've done this. So anywhere in the 3D layout, we can right-click, and then we'll choose Open Optics menu. So from here, we can either search for a specific lens up here, or we can use the added filters to search for some general parameters. Since we know what we have in our outliner, let's go back and search for the first lens in our system. So the first lens is an LA4052 UV fused silica plano convex lens from Thor Labs. All right, so let's go ahead and search for that. Open up the optics menu. Okay. Great. So this has actually pulled up all of the LA4052 lenses from Thor Labs. As you can see, the top one is an uncoated lens, and the ones following in the list have either a V coat or a broadband coat. So let's go ahead and select this first lens and see how it shows up on our system. Okay. So one thing about selecting a lens from the lens catalog is wherever your cursor was last is where the optics will be placed. So my cursor was up here, so the optics actually popped up there. Now, the nice thing about this 3D layout is you can dynamically move around your lens or any other optics. And if we click the Move Rotate button, what you'll see is this line. And this line is drawn to the coordinate surface that this axis is attached to. If we go like this, we can see that is our origin. That is our global coordinate system. And if I drag this around, the line will follow that. So this is a really nice feature to see what our optics are referenced to really quickly without having to go in and kind of see what options we've chosen. We can also check, select a new reference surface. So we'll check one of the other lenses, and we'll go to the back. Every surface has a coordinate system. And if we go back to this lens, we should be able to see, yep, now it's attached to the coordinate system on the back of the second lens. All right, let's go ahead and delete this and move on. That's just kind of a neat feature I wanted to show you really quick. Okay. So now let's look at some of our lens information that we've added to our design. So we can click on the lens either in the outliner or on the lens itself. And then if we do that, we'll go back to the outliner. We can also look at our optical settings. Now, this is going to pull up the prescription of the lens that we've inserted into our optical system. First tab is some basic info, brand, type, shape, and also this nice little web link to the product. So if we click this button here, we'll actually pull up a web page to the optic that we've inserted. And this is kind of nice, especially if you're using lenses or optics all from the same company, because you can go in here and easily add everything to your cart when you're done building up your optical system and easily order it. So that's kind of a nice feature there. All right, moving down to geometrical properties, pretty self-explanatory. We've got the diameter, thickness center, and the radius. Now, you'll notice that these are all changeable. The reason they're changeable is if you need a template lens, then you can use kind of any lens that you find in the stock catalog and change these diameters. And obviously, it'll change the parameters of that lens. It's coming down to material info. So this is a UV fused silica lens. We can see the Sellmeyer equations used, and we can see the different coefficients. A nice little feature here is we can actually see what the parameters are at specific wavelengths. And looks like we have a question. And we can see at the wavelengths that we're using what our index of refraction is, effective focal lengths, and some other information that we get. So this is kind of a nice feature to see what we're going to expect from our lens at different wavelengths. One thing I will warn you, the limits of the lens material is not inserted. So be careful that you don't put in a wavelength that is not accepted by the lens material. So make sure you know what you're putting into these tabs before using them. Okay. And the last surface down here, optical surfaces. This is kind of a nice feature as well, because you'll be able to tell which surface is your front and which surface is your back. So if we look up here in the 3D layout, kind of see a side view of the lens. If we scroll over front and back surface down to the optical surfaces, we can physically see what is the back surface and what is the front. So right now it looks like we have the front curved surface and the plano side is the back. Okay, so that's a kind of a good reference. So if we select one of the optical surfaces and click on them, we'll have a couple more parameters pop up. So we'll have the name of the lens, and we can rename that if we wish. We also have simulation settings and scattering info. We're not going to go over these in this webinar. What we will do later in the webinar is, there we go, is enable the surface shape component. And when we do this, we're going to use the shape model of a Zernike fringe sag. And with this, we'll add a couple terms and we can actually add in some aberrations into a surface in our optical system. But we'll save this for later. Okay, close out of here. All right, so hopefully that's a little bit helpful on how we add optics and kind of how to analyze our optics once they're in. All right. So with this design that we have mocked up currently, what I had done is inserted the lenses, propagated the fields, and then moved the detectors and the lenses around. So everything kind of lined up in a very general sense, a very nominal position. So there's no optimization here, just moving around components visually to get them in what looks like good placements. Note again that we can drag and drop the optics around in the 3D layout, or we can also use the move rotate for some finer adjustments down there. So this is just a great way to move optics around quickly and prototype up your system. Okay, so let's move on to the detectors. So we have some detectors over here, and we're going to use two configurations. It's currently in the first configuration. In the first configuration, we're going to be using the lenses along this line, and this line. So basically columns 1, columns 2, and columns 4. If we hit the propagation simulation button up here, this will propagate the rays from our system. All right, so now we've launched all the rays. We have one errant ray coming over here. That's going to propagate out of the system, so I'm not too worried about that guy. So as we can see, we have a general lineup of the pre-focus, focus, and then post-focus locations for the detectors. Now, we've aligned these detectors based on the on-axis field down here. And from the on-axis field, you can see we're pretty close to the visual focus, and then we are at some distance before and after that. Now, since we're generally every time using flat detectors in a camera or any other detecting system, really you have a flat plane, imaging plane, a detector along here that I've just split up into 3 different little sections. So obviously there are better focus locations elsewhere, but we don't use curved sensors, we use flat sensors, so we do have to line these up. And that's going to help us analyze the aberrations of systems because we want to prototype this as an actual system can be designed. Okay, so let's select one of the detectors. Now again, we can select the detector just like any other object on the 3D layout or on the outliner bar on the left. Either way, we'll pull up the ribbon bar on the right, and it has some very similar parameters here. We can name it, move it around with the move rotate icon, and then we can pull up the parameters. Now, for these parameters, we have the X half width and the Y half width, so very simple parameters to set up. So all the detectors here are the same size. They're 2 millimeters by 2 millimeters, so 1 by 1 if you're looking at the radius or the half width. And they also have 100% transparent. So the transparency is nice if you're wanting to look at the rays and how they interact. Let's do the top view so we can select the detector. So using the transparency is nice if you want to see how the rays are striking the surface of the detector. So we'll click off here, and then we'll zoom in a little bit. Okay. And if we get kind of a front view, we can physically see where those rays are hitting the detector. Now, if we wanted to line up the detector visually perfectly in the middle of the field of the light beam, then we could move this to the left or the right, up and down, however we need to make it, to put it in the correct orientation. But the rays are striking near the center of the detector for this application. That's good enough. So we're going to keep it where it is. All right, so let's zoom out a little bit here. Okay, one last feature I want to go over before we move on is the ability to create any surface as a detector. And what I mean by that is we'll take our biconcave lens here, and we can see that it pulls up in the outliner bar. Now we have a couple options for back, frame, and front. And if we click those, we can see that it has a local coordinate system, so it corresponds to a surface. So the front surface of this biconcave lens is right here. Now, if we care about how our beam is propagating through the system, through our optical system, and we want as much information about that as possible, we can make every surface in our optical system a detecting surface. And we do that by right-clicking and adding the surface as a detecting surface. And you'll see where this goes a little bit later in the analysis, but that will create another detecting surface on the front of the lens here. And in fact, we can make the front and the back and the frame a detecting surface. If we're really wanting to know where the light is going every time it hits an optic, we can do that with this feature. Again, this is a really nice feature, so we can kind of see easily how our beam is propagating through the system. So we're going to go ahead and remove that guy. So hopefully that is useful to some of you. I know it is useful to me if I don't want to put a bunch of detectors everywhere in my system. If I just quickly want to see what's happening, I can use a couple surfaces as detectors and use the analysis on that. Okay, one last item on the detectors here. And you probably saw it when I zoomed in. You'll see this F on the front of the detector. Now this is, the F stands for front, so you'll know where the front of the detector is. If we rotate around, there's a B on the back, obviously for the back of the detector. Now this is nice because as it is, the front of the detector, rotate around here, is the detecting surface. So the rays have to be coming from the front of the detector to be detected. So for instance, if we had for this central field, this 10-degree field here, the blue rays. If the source was coming from the bottom right up to the top left, the back surface, because it is not a detecting surface, there would be nothing on the detector. So it's a good way to quickly check if something's going on with your system, your detector's not updating, maybe the rays are striking the wrong surface. So it's a good kind of sanity check to go through. Okay, so hopefully that is clear on how we set up the system and some of the parameters we used and where they are for this system. All right, so let's move on to the actual aberration analysis portion of our webinar. Okay, so as I had stated earlier, we have a nominal setup here. So all of our lenses and all the detectors are at some nominal position. There's no optimization. We have selected some distances based on having the rays, different rays from the different fields actually propagating through the system. So the way we are going to look at the aberrations in the optical system is using phase maps and spot diagrams. So we're going to go up to the top right or top left where the ribbon bar is, and we're going to click on Analysis Portal. So that will bring up our analysis portal. And as you can see, we have pre-populated 3DOptix interface has pre-populated all the detectors that I've already placed on the layout. So this is automatic. This isn't something I've done before, which is really nice because you don't have to tell it to analyze the surface. It'll analyze all the surface. All you need to tell it is what surfaces to not analyze. And you can do that by simply unclicking one of the detectors. All right, so let's look at some of the parameters we have for our detectors. So for the analysis, we have two options, fast analysis and advanced analysis. The advanced analysis is for our premium users, and the fast analysis is for all users. So we have spot incoherent for the fast, and then spot coherent and incoherent for the advanced and the coherent phase. So we're going to look at the spot diagrams for all the off-axis detectors, and we're going to look at the incoherent spots and also the coherent phase at the focus, or what we believe to be the focus of all the fields. Okay, so let's go to the on-axis focus here, so we can look at some of the options we're working with. So we went over the analysis, and now what you'll see are the different light sources that we have. So we've got 5 light sources, and we can tell 3DOptix how many rays we want to use for analysis for each one of those. So we can set each one separately to whatever we want, depending on our analysis needs. It can be low or high, but we're going to keep all of these the same for now. On the right, you can also select the number. Let's make this a little bit bigger. There we go. You can also select the number of pixels for the detector. Now, this is the full detector width in X and Y, so this is not the radius. Now, one thing to note about the pixels is you don't want to have too many pixels on your detector. If you have a very, very large detector and you have 1,000 pixels, but you only have 10,000 light rays hitting that detector, and each pixel only gets 1 light ray, then you're going to have a less accurate spatial intensity map. So make sure that when you're selecting the amount of pixels, that is appropriate for how many rays that you're propagating through for your system. Now, in addition to that, for our most advanced licenses, we can have up to 10,000 pixels in each dimension. But again, because I know that we don't need that many, we're going to keep these at 1,000. And this is just because the beam is very small on focus. Okay. Now let's start the analysis with the Run Analysis button here at the bottom. And before we do that, I'll go over the turbo button. So the turbo button allows us to speed up the analysis. And you'll have this nice little pop-up that tells you kind of what's going on. So if you do hit the turbo button, you're going to use resources at twice the normal speed. And as we know, we only have so many resources, GPU resources here. So this is useful for really long analyses, or if we have a lot of detectors and it's taking a long time to get the analysis completed. For today, we're not going to need that, so we're just going to do a normal analysis run. And we also have a terminate button just in case we choose not to, or if something is taking too long. All right, we'll hit the run analysis. So I do want to point out that apologies. So I do want to point out that the GPU usage down here, when we click the analysis button, it'll start using our resources. When the analysis is completed, it actually won't let you rerun the analysis and then therefore burn through GPU time if there's nothing new. So that's kind of a nice feature, a great implementation, because if I keep on running this and it's the same over and over again, well, then I'm wasting a lot of resources and I'm not getting anything from it. So this actually won't let you run the new analysis unless something in your optical system has changed. That's a really great feature about this. I do want to point out that the benefit of this and the 3DOptix web-based application and cloud computing is that there are no special hardware requirements and the GPU resources needed to ray trace are done externally. So if you need rapid optical prototyping, design collaboration, or sharing and low hardware requirements, this is just a great solution. Sharing designs with clients, I really want to stress, is a great use case because not everybody has a high-end computer to trace rays and look at some of the more advanced optical systems. Okay, so now that the analysis is complete, let's look at the on-axis field and see what we can see. So we will select on-axis post focus, and we're going to use this compare feature here. So we're going to click the compare button. So it'll allow us to compare multiple windows. We'll find the other on-axis. We have a pre-focus here. Oops. And also an on-axis focus. So we'll compare that, and also we'll look at the phase map because we want to see what the phase map looks like at the focus. Okay, so now that we've selected the on-axis fields, so the pre-focus, focus, and post-focus, we'll hit this compare selected button. All right, so that will pull up a nice little layout of what we've selected. As you can see, we've got our analysis windows here. It's a little bit small, so what we're going to do is click on each one of them, and they're going to pop up a new analysis window here so we can resize them and make them a little bit bigger. Okay, so we're going to close this guy out here because we don't need it anymore. So let's pull our analysis windows over here so we can look at them. They do snap together, so I don't know if you can see that, but that's a nice little feature there so they don't, so they're not just free floating over the screen. Okay, so as we can see, we've got our pre-focus converging beam, and then at the focus, we've got a very small spot size. That looks great. And then post-focus, we have something diverging coming out. And then down here on the bottom, we have the phase front. And that looks pretty good. This is the on-axis field, so this really makes a lot of sense, right? We shouldn't see many aberrations at all, maybe definitely a little bit of spherical depending on the height of the rays. Okay, so this all really looks good. Everything on axis makes a lot of sense, and this is a good starting point. This is kind of a good sanity check for us, so we can say, yes, the kind of on-axis beam looks good, so we can look at the off-axis, see what's going on there, knowing we have a good setup. All right, before we move on to the other fields, I do want to go over a couple options here in the analysis windows. So the first one up here is the little tab bar. So we can lock the design. So if we want to lock this and rerun the analysis, it just won't rerun this field or this window. And this lock button is also tied to the analysis portal. So if we look at on-axis focus down here, since we've selected lock here, it'll also lock this and vice versa. There we go. We have the zoom in and zoom out. You can use those buttons, or as you've seen me do, you can just drag and drop using the left mouse key. We've got the reset button if we go in too far. We can also see the wavelengths hitting the detector. Again, right now we only have 550 nanometer monochromatic light hitting it. The last is the display type. So we can do false color, what you're seeing now, or grayscale. Very similar designs. Reset that. And we can also do a spectral view if we've got polychromatic sources. Obviously, this is not, so we're going to get one green. Oops, sorry about that. There we go. So we get one green dot. And the last part is the XY cross section. So you can actually look at the irradiance at a certain point in the optical system. Close that out. That'll pop back up if we left click anywhere in the optical system. So let's get this cross section down here, coordinate value, and then the incoherent irradiance. Another thing we can do is actually change the pixels ourselves instead of just dropping the cursor around. That'll show you with these crosshairs where you're looking down here. So a nice little feature if you're wondering how the intensity is varying over your system, or you need a specific pixel value. All right, so let's go back to false color. And down here in the 3 lines bar down, we can also do a linear view, which is what we're looking at now, or a logarithmic view. Okay, so we've gone over those. Let's go back and look at the other fields. So we have a 10-degree off-axis field and a 20-degree field. So let's look at the 10-degree field. We're going to uncompare these really quick. All right, and instead of comparing these, we're just going to pop up the analyses window so we can see them a little bit better. The pre-focus field here, pop that up, and then finally the post-focus field. Okay, so we're going to do the same thing. We'll drag these guys to the left and the right so we can see what's going on with the beam and look at the aberrations if we can see any. Okay, great. All right, so we definitely have an aberrated beam here. So this is the 10-degree field, and we can see we've got possibly some astigmatism, some coma, spherical aberration, all kind of in the beam. You see the post-focus or the pre-focus, definitely some coma from this. All right, let's go look at the phase diagram here, and we can definitely see some coma from here. And then there are multiple other aberrations kind of coming all together to give us this weird phase profile. Ideally, we want concentric rings, but obviously the off-axis beam, since we haven't corrected any aberrations, is going to look aberrated. So this is great. We can actually see that we have an aberrated beam, and we can compare it with the on-axis field to see that there's an actual difference. Okay, so lastly, let's go on to the 20-degree field. So we have post focus here, and again, we'll do the same thing. We'll just click and open up the windows. 20-degree pre-focus, and then 20-degree focus. There we go. And again, we'll open up the phase map for that guy. Here's the focus, here's the pre-focus, and here's the post-focus as usual. Line these up, okay, and then we have a much more aberrated beam here. All right, so we can physically see from the spot diagrams that we're having an aberrated beam. And then the phase plot is definitely aberrated. We're seeing a little bit of that coma and other aberrations here as well. Okay, great. So again, this is a good way to kind of get a visual basic analysis of the aberrations in your system. Having an on-axis and some off-axis beams, we can definitely see that there are aberrations in the system. Kind of a quick check. All right, so now we're going to change the orientation of our lens system. So we're actually going to move the last lens in our system here. We'll pull this guy down. We're going to move this last lens a little farther out, and we're going to see what happens to the optical system. If it's better, worse, or no change. Before we do that, we are going to look at the focus, and we're going to lock the focus of each of the fields so we can compare them. So there's our 20-degree focus. There's our on-axis focus. We'll lock that as well. Okay, and then our 10-degree focus. It's nice that all the focus are at the bottom of the analysis portal. Okay, we'll lock this guy as well. Now we're going to downsize these so we have a little bit more room to work with. Just to note, the minimize windows are over here, and if you just click them, they'll pop right back up. Okay, fantastic. All right, so now we will select our lens in the outliner bar. Go ahead and close this as well. We'll go up here to the ribbon and use the move rotate button to move the lens. We'll only move it 3 millimeters. Don't need to go too far. We want to make sure that all the fields will propagate through. Okay. Now, if we propagate through, we should see the fields lining up with the second set of detectors in this configuration. Okay, great. So again, the third column here is the second set of detectors, and it looks like they're lining up still. Good, so we placed our detectors in the right spot. Let's go back to the analysis window. I'll have to answer that question later. Okay, so now we have these 3 detectors we want to look at in addition to our lock detectors. So we're going to run the analysis. And again, I could have turned off the other detectors, but the analysis doesn't take that long, so we'll just keep them all on just for time's sake. All right. Now that our analysis is done, we'll start pulling up the shifted detectors. All right. These guys, we can look at the phase maps really quick as well. So the shifted 20-degree focus, and we have a shifted 10-degree focus. Okay. And then we have shifted on-axis focus. There we go. All right, so pull these guys up. And we'll close down the analysis window for a second here. So shifted on axis, so we have a little bit more room. There we go. All right, get everything lined up so we can kind of see everything in line. I do want to move these around in order, make it better to see that way. There we go. All right, so we've got on axis 10 degrees and 20 degrees. Let's see what's going on here. And I had everything backwards. All right, let's move everything to the correct spot. Okay, so as we can see, the on axis really shouldn't change much. We've changed the lens, a little bit more spherical aberration maybe, but not really too much to look at. And then obviously the 10 and the 20-degree fields look a little bit the same, but now we can actually look at the other analyses from the previous to see how they've changed. And just to mention down here, the phase maps are just showing a little bit more aberration here. So we can kind of see everything got possibly a little bit worse is what it's looking like. All right, so let's close off the phase maps. Let's open the detectors really quick from the previous analysis. So this is on axis, and this is 20. All right. Again, on axis is not going to change much. However, this 10-degree field and 20-degree field have definitely changed. So since the on axis hasn't changed, we'll get rid of those. As we can see, the energy is definitely a little bit more asymmetric. So we're getting a little bit more aberrated from the beam. So this could be from the focal point we've chosen for our detector, or it could be just from the included aberration from moving the lens around. But they are definitely more aberrated now than they were previously. All right, so that's great. So that gives us a good analysis to see that we've moved to the wrong position. So if I were actually mocking up the system, prototyping it, I would go back to where I had my lenses in this configuration saying, well, this looks a lot better, and this would be a really good starting point for me. So again, this gives you kind of a visual analysis of what your optical system is doing in a rough sense and kind of where a good starting point is for your system. Okay, so the next thing we're going to do is we're going to look at the surface shape that I had mentioned earlier in the webinar. So we're going to move the lens back to its previous position, down in 21. Okay. And then we will repropagate the rays. Okay, now they're going through the detectors in this line again. Okay, great. So we've got everything set up as we had it previously. Now we're going to click on this lens just like we did. Go up here to the outliner, just because it's easier to click on the outliner. And we'll go to the optical settings. We will click again on the front surface. And we're going to enable that surface shape component. Go down here and select the Zernike fringe sag. And for this, we're going to go over a couple of these terms. So we're going to first start with astigmatism. So we're going to go up to term 4. And the third term is going to be our oblique astigmatism. So let's make that 0.1 millimeters. Okay. We'll close this. And then we will go back up to the analysis portal so we can see what happened on the on-axis beam for the astigmatism. Oh, and I should mention, we're just going to use the on-axis beam because it'll give us a clear picture since there's very little aberrations on what's going on. So let's go ahead and run the analysis. Again, we can deselect some of these detectors, but since we have so few, it's a bit faster just to run the analysis and let all the windows update. Okay, looks like the analysis is done. So let's go to the on-axis field and pull up the spot diagrams. Let's post focus. And we've got on-axis focus. And the phase map. Okay. And the on-axis pre-focus. There we go. Fantastic. All right. Let's move this guy down a little bit. Move this in line. Again, these nicely snap together. Okay, great. So we've introduced astigmatism into our beam, and we can definitely see that on the input and the output beam. Here in the center, a little bit, not really. More with a phase map, we can kind of see the profile, but the post focus and the pre-focus, actually I want to move those guys around to get them in the proper orientation. But the pre-focus and the post-focus, we can definitely see that astigmatism. All right, great. So let's go back to our lens. We're going to go back to optical settings. Let's downsize these guys so we can see what we're doing. Let's go back to optical surfaces. Now we're going to go to the 5th term. Set the oblique to 0. Now we're going to do horizontal, which is the 5th term. And we'll do the same amount of astigmatism, 0.1 millimeters. We will quickly run the analysis. And we'll pull up our analysis windows and see what happens. Okay, great. So we actually get horizontal astigmatism. Perfect. Phase map changed a little bit, but we can definitely see that we have a stigma in the horizontal direction here. Fantastic. Okay, so I'd like to go over one more. So we'll minimize these again. Optical settings, go back to the front surface. Do one more, we'll do oblique coma, which is the 8th term here. Setting this to 0. All right, and the oblique term, 0.1. We'll go back and yet again, run the analysis. Okay, let's bring back our analyses and see what happens. Okay, kind of gets off the screen, but we definitely see the oblique coma. Fantastic. So this we wanted to show as it's a really good way first to see different types and weights of aberrations in your lens, what would happen at the output. And also it's a good feature if you know what your real world system looks like, you can actually try to model this in 3DOptix using Zernike sag fringe surface, or one of the other surface shapes that we have here. So it's a really nice feature. Again, if you're trying to quickly figure out what's going on with your system, you can rapidly prototype it in 3DOptix and start playing around with the aberrations to see what's going on with your system. Again, it's really nice that this is so fast and you don't have any hardware requirements. Everything is done, outside of your computer. The analysis is quick. Building up the system is quick, and doing some of the deep dive analysis to see what's going on in your system is very quick as well. Okay, so I've run out of time here. So this is going to conclude my analysis portion of the 3DOptix webinar. I want to thank everybody for joining us today, navigating and getting familiar with web-based platform that is 3DOptix. I really hope you found some of this useful, or at least are more familiar with the platform now. So I'm going to hand this back over to Gil and let him close up.
Okay, Keith, thank you very much. It was really fascinating how a designer very quickly from the day that you started to work with the platform ramped up with your knowledge and excited to have such a great design. So thank you very much. I do want to close this session and say two more things. One, I was asked about recording, and I know that we had a lot of registration that didn't attend. We're going to send a link to the recording of this session, so it will be available. That's one thing. And the next thing, that we would like to provide all of our users a complimentary additional discount, and it is available for the next 48 hours on our website. So if you hurry up, so you get an additional discount. It's for $800. You get the standard license. So if you hurry up, you can get that. I do see that we have two more questions. No, I think that is done. So this is, by the way, we do have a few more minutes. If you have any questions, so feel free to write those. Is it straightforward to export the array bundles to CAD software? So currently, it is not allowed. We don't provide any way to export the array bundles to CAD, but this is something that we are working right now, and it will be available pretty soon, that feature. Yes, we do have student license. So if you look at the pricing website, on the page on our website, you will see on the pricing page. So for students, it is the same price as a standard user, but you get 5 seats for one price. So it's 5 for 1. So this is a student, so it would suit an entire lab. You'd get 5 licenses. Any more questions? This is the time right now. Okay, so thank you very much again. I would like to give you a heads up of what is expected in about 2 weeks. We are going to have the first optical hackathon in 2 weeks. We will send notification for the community. It will be with prizes, of course, to do some designs, and you will get the first, the second, and the third, and places will get some nice prizes. So thank you very much for participating, and see you on our next event. Bye, guys.